Hi, I'm Robert Kaplinsky, and I'm grateful for this opportunity to talk to you about something I'm really passionate about. So, as math educators, it can be challenging because you want to know what your students understand. And oftentimes we'll ask them a problem, a math problem, and get an answer back. And if they get the correct answer, then, I guess they understand what they're talking about. But we've also probably had that experience where a kid gets a correct answer, and then later we discover they don't really know what they're talking about. And this is really tricky because how do we uncover this? Because you don't want to find out, after the quiz, after the test, after the state standardized assessment, when you find out they didn't understand that. And so that's something I really want to talk about in this presentation, which is how do we formatively assess our students in real time so we can uncover these hidden misconceptions? And now the challenge here is that sometimes, they don't know that they don't know. Maybe they do know and they're just kind of embarrassed to talk about it, but sometimes there's legitimate situations where they think they understand, but they don't understand. And that's really tough to uncover because just asking them whether they need help, well, they say they don't. So how do you know when they really need that help? So the way we're going to explore this is I'm going to begin by telling you some stories that I think really give us some context for how this will actually take place. And then we'll talk about how to specifically apply this to math education. So we'll begin actually with this story first about King Solomon. So King Solomon had this situation where two women claimed to be the mother of a single child. And there's no DNA testing or anything like that. So how do you determine who is the mother? So he's talking to both of them and it's getting nowhere. And in frustration, he says something that terrifies people. He says to bring him his sword so he can cut the baby in half and give half the child to both of the women. So this is a little bit heavy-handed here. And what happens next that gives him all the information that he really needs. One woman says, sure, cut the baby in half. And the other woman says, no, she can have the child. And that was all the information that he needed. Because as terrible as it would be for a parent to lose their child, it'd be far worse to have the baby slaughtered. And so what's important to realize here is that you had King Solomon, sort of the teacher here, trying to do formative assessment and figure out what is really going on here. You have one woman who's actively trying to not share what's going on, and the other woman who is, but you can't tell who's who. So he devised a situation that helped him uncover the information that he needs so he can act accordingly, even when one was not a willing participant. So that's really what we're going to try to focus on here. What does this look like in math education? Let's talk about another example, Van Halen. You wouldn't think this is connected, and these stories come from the Freakonomic podcast. I love that podcast, and it really inspired my thinking about what this might look like in math education. So they talked about how Van Halen, this is one of the biggest rock bands of the 80s. Now, prior to Van Halen, most of what we now consider standard practice in concerts, well, it wasn't like that. Concerts used to look like, maybe if you remember the movie Back to the Future, where you had an elevated stage and maybe some sort of auditorium, and the band stood up there and then played, and everyone listened. But when Van Halen came around, they did it way different. They had whole walls of light and sound and pyrotechnics, and this was very new. But now I want you to think about the challenge that Van Halen faced. They're doing world tours. They're taking this equipment and shipping it all over. All different venues are having to set this up. And now, if you realize this, this is a lot of equipment. If this is not installed properly and it comes crashing down, someone's going to get injured or worse. So when Van Halen asked the venue, hey, did you follow what's in our contract and set up the equipment properly? What do you think they're going to say? They're going to say, yeah, we did. And this is going to range from anywhere from they know they didn't and they are saying that they did, to they truly did set up correctly, to ones in the middle where they think that they set up correctly but maybe missed a detail. How do you discern this? So Van Halen came up with a deviously clever plan. Now you maybe are familiar with rock stars having clauses in their contract that require all sorts of zany things. Maybe the room to be set to a specific temperature or certain kinds of flowers or foods or beverages. So Van Halen put a clause in there saying that there need to be, now some of you may be too young to remember that there was a time before blue M&Ms where they had brown M&Ms, but Van Halen in their contract said in bold, capital, underlined letters, absolutely no brown M&Ms in a bowl of M&Ms. So I want you to think about what Van Halen did next. They would go to the concert venue, they would go to their dressing room and check the M&Ms. Now, if there were no brown M&Ms, it wasn't a guarantee that everything was fine, but you'd start to think that they probably were paying attention to the details. And if you did see brown M&Ms, you'd think, well, if they can't even get that right, we should really double check all our equipment. So again, the theme here is this. People are coming up with a clever way to get the information that they need to make the appropriate decisions. And in math education, as teachers, that can be really challenging, whether students are intentionally or unintentionally telling us what we need to know. So how do we get that information? Because I think that historically, we think we're pretty good at it. Like, you ask a kid a question, if they get it wrong, they don't know. If they get it right, they do know. But sometimes the ways that we have tried to acquire that information gives us these false positive situations. And I want to share one more example of what a false positive might look like. So this is Nigel Richards. He won the French Scrabble tournament. Now, someone who won the Scrabble tournament would be like quite a brilliant person. If you're not familiar with Scrabble, it's a board game that you play by making words that have point values. Each of the wooden tiles has a letter and an associated point value, and you place them on squares to try to make the most points you can get, and that's how you win. So if someone is crushing Scrabble, they must like be masters of that language. Like, how do you, of course, right? So what's really interesting about Nigel Richards is that he won the French Scrabble tournament and he does not speak French. Like, what? Like, can you just imagine playing Nigel, you're in this tournament with him and he's crushing you and you're like trying to talk to him and he has no idea what you're saying because he doesn't speak French. Like, how would you process that? That'd be so humbling. And I'm sharing this because, again, at a glance, you'd think, oh, if you know French well enough to win the French Scrabble tournament, you must be a master of the language. But sometimes the way we measure mastery gives us this false positive information. And it's not impossible to figure out that he doesn't know French, but you have to measure it in a certain way. And that's really what I want to explore in math education, which is how do we put students in a situation where we can really see what they know. Now, I'm not here to tell you this is the right way to teach it or this is the right way to fix the problem, but I am here to share with you strategies that will help you get information that you can actually use in real time. So the strategy I'm going to recommend highly is a strategy called open middle math problems. These are problems that teachers have been using for nearly a decade, and teachers love them, and I think you will love them too. So let me take you through an example so you can get a feel for what it's like. This is an open middle problem, and I'm going to read it to you. It says, using the digits 1 to 9 at most one time each, place a digit in each box to create a fraction that is as close to 1 as possible. Now, you cannot use 0, you cannot repeat a digit, and you can't do like 1, 1 over 1, 1. But you want to make a fraction that's as close to 1 as possible. So like as an example, you might put 1 and 2 in the numerator, and now you've got a 12, and a 3 and a 4 in the denominator, and now you've got a 34. 12 over 34 is not like the worst fraction from 1, but I'm sure you could think of a way to place digits to get you a fraction that's even closer to 1. This is also not the Price is Right, so a little bit above 1, a little bit below 1. They're both great. So here's what I'm going to do. I'm going to give you 3 minutes or so to practice this. Feel free to use a calculator. That's totally fine. And I want you just to start experimenting with this and start thinking about, what would be a good fraction to create there? And then we're going to come back together. You'll see that there are blue zigzags at the bottom. As they turn to green, we're going to come back together and you'll know that the time is running out. Now, if you're feeling like you have a fraction and you're already ready to go, this is something you got, here's what I would like you to do. Take whatever fraction you have right now that you're feeling really confident about, and next to it, write the reciprocal. So if it was like, say, 12 over 34, now you're writing 34 over 12. Which of those two fractions is closer to 1? Are they both equivalent in terms of the distance from 1? Are they both equally far from 1? Or is one of those closer? We'll come back together in just a little bit now. All right, so let's unpack this. How do people approach this problem? There's usually two paths that people might take, and they might do them simultaneously, so let's unpack each one. One of the first realizations that people have is that you want the value of the numerator and the value of the denominator to be as close together as possible. So you might have gotten something like 29 over 31, or 39 over 41, or 49 over 51, or something like that, somewhere along in the process. Another realization that you have is that you want the value of the denominator to be as large as possible, because that means that any of the missing pieces will be very small. And so you see things like, large values, 90s, 80s, 70s in the denominator. Eventually, you usually wind up on two answers that are pretty common. The first one is 81 over 79. And the second one is 79 over 81. And I'd like you to actually write both of those down somewhere on a piece of paper. 81 over 79 and 79 over 81. And what I would like to now do in terms of extending this problem is ask you a related question, which is this. Which of these two fractions are closer to 1? And when I do this question with large groups of teachers, I inevitably get all three of these answers as possible. And the three answers are 81 over 79 is closer to 1, 79 over 81 is closer to 1, or they are both equally close to 1. So I'm going to give you a minute or so to think about this. Feel free to use a calculator again, feel free to use any tools that you like, but think deeply for a second. Which of these is closer to 1, or are they both equally close to 1? And then we'll come back together in just a little bit. All right, so let's talk about this. There are a lot of ways to unpack this, but here's the really important takeaway here. You might be thinking, why is he even asking this? I know which one is closer to 1. Let's move on. But the thing I think is really important here is that when you do this with students, especially with larger groups of students, you will get all three of these answers. And if you don't know how all three of these answers could be gotten, and it's not just like people guessing, but legitimately think that they're right, you're probably not ready to teach this lesson. And just for experience, I still have mess ups when I teach lessons. And one of the things I consistently find as the root reason why my lessons flop is that I did not spend enough time anticipating how kids might solve the problem. I thought every kid's going to do it my way. It's so obvious. And then when they do it some other way, whether it's right or wrong, I have no idea what the hell they did. And so I'm just sitting there trying to figure that out instead of trying to help kids. So spending time anticipating what kids will actually do is very valuable. So let's go through each one, and I want you really to think deeply of, could students do this, and what would I do if that happened? So the first way that kids typically might, or not, rather the first way, a way that people might do this, and it's very painful, is try to find common denominators. So they might do both these fractions and then multiply them by 1, which is 79 over 79, or 81 over 81 in this case, and you get these fractions. But like, even right now, it's not clear which of these is closer to 1. You might say, let me just subtract the numerator and the denominator, but then you get these values, and even here, is 158 closer to 1? Is that a better thing because it's a smaller absolute value, or is it negative 162 because it's a lower number? It's not clear always. Some people will use a calculator. They'll say, well, 79 divided by 81 gives me basically like 25 thousandths away and then 3 and some other stuff. And then they might do 81 over 79 and get the same thing, 25 thousandths and then 3 and some other stuff. So again, suspending disbelief if you don't agree with me right now, you could see that if you just round or kind of ignore the rest of it, you might come to this conclusion that they're equivalent. They're both basically 25 thousandths away. So we can at the very least see how someone might come to that conclusion. Next, let's explore how people get 81 over 79. I want you not to round, but to chop. Let's just chop at the hundredths place. So if we were taking 81 over 79 and just chopped it at the hundredths place, again, not rounding, then this becomes 1 and 200ths, and it's only 2 hundredths away from 1. Let's now look at the other one. If we chop this, again, not rounded, but chopped 79 divided by 81, this is 97 hundredths, which is 3 hundredths away. So in this case, 81 over 79 is clearly closer. And it's important just again to see like where are the kids coming from, because you want to not only know when kids have misconceptions, but understand why they have misconceptions so you can fix them. And then some kids will, either be very precise with the calculator or they will think about it conceptually. So both of these fractions, 79 over 81 and 81 over 79, are 2 units away from 1. But what really matters here is 2 what's. In the case of 79 over 81, it is 2 81ths away from 1. But with 81 over 79, it is 2 79ths away from 1. And even right here, you might have people like not sure what to do with it. Do I look at the 81st or the 79ths? But when you think about it, 2 81ths are smaller than 2 79ths. So 79 over 81 has to be closer to 1. And this is the first example of kind of what we're talking about. This King Solomon Van Halen situation where kids might be great. They might be able to crush a worksheet of comparing fractions. But at the same time, students, and even if we're being honest, adults will struggle with this problem. And so we have misconceptions that may be even hidden from us as math educators. So this open middle problem brought out a hidden misconception. If it's not you, it's somebody else, but it brings out hidden misconceptions that you can now see more clearly and do something about. Let's look at another example. This one is for younger grades. So using the digits 1 to 9 at most 1 time each, place a digit in each box to make the greatest possible sum. I'm only going to give you 20 seconds this time, but I want you to think about this and then we'll come back together. All right, so thinking about this, kids will typically know which digits to use, but maybe not necessarily where to put them. And what you commonly see is what I saw the first time I used this problem with my son. Now he's going into 10th grade, but he used to be a little kid. And I think I gave this to him when he was in 1st grade. And here is what he put. He put 9, 8, 7, and 6. So you might have gotten this, or you might have not gotten this, but you can see why someone would have picked this. There's a lot of brilliance here, right? He knows which digits to use, but maybe there's a misconception here. So I ask him questions. I say, what does the 9 represent? And he says, it's 9 tens. And the 8, it's 8 ones, 7 tens, and 6 ones. And I ask him, would you rather have... So right now, I see that he's not maximizing his values by where he places the digit. So I ask him this question, would you rather have more tens or more ones? And he sits and he thinks, and it's like, oh. And he realizes, okay, the 9 can go here, but the 8 needs to go there. And then the 7 and 6 can go wherever you want. And so again, the theme here is that if I had given him a worksheet of 2-digit addition problems, he would have obliterated. He was crushing that at the time. But he had misconceptions that I didn't see and he didn't see. And this allowed me to spot the hidden misconception and fix it. Let's look at another example. This is a very typical problem for area and perimeter. What is the perimeter of a rectangle that measures 8 units by 4 units? Like, no one's shocked by the beauty of this problem. But I now want to show you a recording of an 8th grader that I asked to solve this problem. So let's take a look.
What is the perimeter of a rectangle that measures 8 units by 4 units?
24 units.
Okay, how do you know?
Because when you're solving perimeter, you're supposed to add all the sides up.
So this problem basically looks like stuff you see in your textbook, stuff you see on your state standardized assessments. It's not shocking. Based on how he responded, it seems like he understands, right? He understands that perimeter means the length around the outside, that you have to add them up, and that Even if you know two sides of the rectangle, as long as they're not the same side, the parallel sides, then you know that you can find out the entire perimeter. What more could you ask for? And that's really where we're at, where what misconceptions are there? Like what else? Move on, this kid knows it. But I want to point out that sometimes there are misconceptions that are not always obvious. So I asked the same student a slightly different question. This one says, list the dimensions of a rectangle with a perimeter of 24 units. So there's a bunch of these. Let's watch the same student answer this question seconds later.
List the dimensions of a rectangle with a perimeter of 24 units. Okay, and how long are the other sides?
The other sides will be smaller than this number because...
So this side is 24 units long?
Yeah.
And then how long is this side?
24.
And how long are these sides?
Let's say about 18 units.
Can you label them, please? Okay, thank you very much.
Like what just happened there, right? This is the same student seconds later. What the heck just happened here? And I think this is really where I'm trying to take us to, which is just the reality that sometimes the questions we ask don't give us the information that we need, but we're so dang used to it because that's the way we've always done it that we don't know what's missing. It's worth noting that the first question was depth of knowledge level 1. The second question was depth of knowledge level 2. This makes us question everything we think we know about this kid. Like, does he even understand what perimeter means? Does he understand that the sides, I mean, like, what is going on here? And again, it's not my intention to say, this is the right way to teach it, this is the right way to fix it. My only goal here is to show you that some kinds of questions are better at helping us spot these hidden misconceptions. And just like with King Solomon or Van Halen, we're asking a question that helps us uncover information even when the child doesn't know that they don't know. So this is an open middle problem. Let's keep going. So the first one was depth of knowledge level 1. This was depth of knowledge level 2. Let's now look at what this might look like with depth of knowledge level 3. So this one says, what is the greatest area you can make from a rectangle with a perimeter of 24 units? So I'm going to give you about a minute to think about this one and then we'll come back together. So as you're wrapping this up, I want you to be thinking about, like, first off, there are lots of possible rectangles here again, right? Because you might be thinking just whole number sides, but if you think about, like, I don't know, a side that's 1.5, that will absolutely work. So there's a lot of possibilities here. And if you have just procedural skills, but no kind of conceptual understanding, this can take a while. So I think you could really imagine kids who maybe understand in general rectangle, area, and perimeter and still get this one wrong, which makes you then think, like, did they really understand that? So I want to now share with you my favorite work sample I've ever received in my entire career in education. Let's walk through it. So this one is from an 8th grade girl. Again, this is an elementary problem, so it's just putting that in perspective. This is on a sheet that we call the open middle worksheet. So it's got first attempt, second attempt, and third attempt on the front, and fourth, fifth, and sixth attempt on the back. It's a really great tool to help kids build a growth mindset because oftentimes we have this messaging in math education that if you don't get it right the first time, I guess you're not a math person. But this begins by saying, hey guys, this is a meaty problem. It's going to take many attempts, maybe even 6 attempts. You'll notice in the top right, it says 2 points for each attempt and 2 points for each explanation. This is where I lie to children. You think I'm joking, but I'm not. I tell kids, I hope you don't get it right on the first try because you're only going to get 2 points for each point, 2 points for each explanation. So that's going to be 4 points total. And it creates this kind of weird incentive to, like, oh, I guess I should keep trying. And the lie part is I never grade these, but they don't know that. So here's where we're at. First attempt of drawing a rectangle with the greatest possible area that has a perimeter of 24, she's not even able to draw that rectangle. And I think it's valuable to realize, like, traditionally you would just stop here, like, I can't even do one rectangle with the right perimeter, might as well give up. But she's incentivized to keep going, so she continues. Her next attempt, she gets a 4 by 8. She gets an area of 32 square units. She thinks that there might be a bigger one, so she keeps trying. Now, why did she choose 10? Well, 10's a bigger number, so obviously the area is going to be bigger, except it's not. So she gets an area of 20. Undeterred, she tries 11 by 1. Now, it's at this point that, like, everything clicks in and my X-ray vision tells me, oh, they have misconceptions. I realize that they are understanding that area means multiply, but they don't understand, like, what does the area represent? What does that number that you get represent? So I have them draw me an 11 by 1 rectangle and a 10 by 2 rectangle. And I ask them, where are the square units? Like, show me the 11 and show me the 20. And they draw them out. And they start to realize, oh my gosh, like, one extra column is totally not worth it. It's way better to have another row. And that's where this line comes in the strategy. Use numbers with more than one row. So in her 5th attempt, again, not drawn to scale, but 5 by 7, and then finally 6 by 6. And I love this because, like, traditionally you would just give up after the first one, but this is incentivized to really think deeply about these kinds of problems, to really think about, what are we trying to go for here? And again, the theme is that the kinds of problems that you see traditionally in your textbook, traditionally in your state standardized assessments, maybe in your district common assessments, well, they don't always give you the information that you need. And that's not ideal. So kind of what I would like to kind of just end with is reflecting on is, why do we ask questions? Sometimes we ask questions and where do we get them from? We ask questions, I love this quote from Bob Stake. He says, it's my favorite quote for understanding the difference between formative and summative assessment. When the chef tastes the soup, that's formative. When the customer tastes the soup, that's summative. So when the chef is tasting the soup, they're not tasting it to eat it. They're tasting it to know, do I need more salt or butter or garlic or whatever? I don't know why we put butter in a soup, but let's just ignore that one. And then for this situation, and when a customer tastes the soup, it's done. Like, there's nothing else to do. They're tasting it, it's done. These kinds of problems, they work well for formative and summative assessment, but I love them for formative assessment because you can ask really quickly questions that will give you information that you can now do something with. You don't have to find out later on when they're in the next grade or after a state test. You can get that information while you still have time to do something about it. So I hope this has been useful for you. If you would like to follow up with me, if you've got questions for me, you can reach out to me on social media. I'm at Robert Kaplinsky, but I hope this has been really useful for you. Definitely head over to openmiddle.com. There you will find hundreds of these problems from kindergarten through calculus. They're all free and ready for you to download. You can download the Open Middle worksheet there as well. We've got versions in English, Spanish, and French. We have them in 3 different formats. One is a PDF copy that's for students, which is the one you saw in the work sample. We've got one that's a little bit different that is better for displaying on a document camera. And we have a Google Doc version. There are PDF blackline masters of number tiles. If you have kids when they're first starting, they might repeat numbers by accident. So it's nice to have that physical manipulative. And I also have created matrices of these problems. Like, if you like the contrast between the first, the second, and the third problem, the third problem, by the way, was depth of knowledge level 3. So if you like that contrast between the 3, I've made matrices with all of these from kindergarten through calculus, and they're available on my website. That website is robertkaplinsky.com. If you go under problems and click on Open Middle Problems, you'll find them all there. So again, thank you so much for your time. I really appreciated you listening to me. Hey everyone. So I can see your questions. Thanks for checking out this video. It's kind of weird to not be able to reply to you guys in real time. So I'm going to go through the questions. Hey Marion and hey Linda. Sharmila, you asked about where we can get the slide deck. So I can't type into the chat. So if you can write this down, if you go to robertkaplinsky.com/engaging, robertkaplinsky.com/engaging. I don't have this exact presentation. I customized this for a 30-minute situation, but I've got a very similar presentation that has the same slides in it. So if you go to robertkaplinsky.com/engaging, you'll find it there. Let's see what else. Vanessa, you mentioned something similar, getting a copy of the handout, so you can find it there. Andy, thanks for the assist there. Yeah, so if you go to openmiddle.com, you'll see on the right side, we have everything we talked about, right? It was the English, Spanish, French version. document camera version. Andy is linking to the student version. And there's a Google Doc version, I think. Yeah, exactly that. Thank you, Marion, for mentioning the Open Middle book. So I wrote a book on these kinds of math problems called Open Middle Math Problems That Unlock Student Thinking. It's specifically for grades 6 through 12, but really the book is K-12, like this presentation was K-12, but it's really hard to put like examples from all grade levels in a single book. So we focus on examples from secondary, but really everything works for that. What else? Have I missed anything here? Thank you guys for the kind words. Thank you, Lisa, for, yeah, this is a Berkeley Average shirt, but I think it's important to make sure that people know that everyone is a math person. Some people want to know maybe where can you find more open middle problems. So I'll give you a couple ways to get started. Let's say you like these ideas, but you're not really sure where to get started, or maybe you like these ideas, but you want to help your colleagues get started. So if you go to openmiddle.com, on the homepage, there is a button that you can click that is the Open Middle Starter Pack. So it's a single PDF that has open middle problems from kindergarten through calculus. It talks about what the problem is, the grade level of standard, why we like it, hints, things you should consider. And it's a really great way to just kind of get exposed to what this looks like at different grade levels. If you want to go deeper and see what it looks like specifically at your grade level, again, if you go to robertkaplinsky.com, under the problems section of the menu, there's one for open middle problems. And I've made matrices from these. I've got ones for elementary, secondary, and ones that are elementary only with like K2 on the front and 3-5 on the back, ones that are secondary only, which has, what is it, middle school in the front and high school in the back. And then I've got grade level specific ones for 3rd, 4th, 5th, 6th, all the way through Algebra 2. Nothing for K1, 2 yet, or for stats and calculus. What else? Yeah, that's about it. Oh, also, if you, for some reason, use like Google Classroom or Teach Remotely, or want Google Slide versions of these problems, you can go to openmiddle.com. There's a blue section with a gray button that says like get the Google Slide versions of every problem. So if you get other questions, you can pop them into the chat. But otherwise, I just really appreciate that in these busy times, you make time for this. Did my sound go out? Oh no, I hope my sound didn't go out. But I think we're about to wrap up in a little bit anyway. Yeah, I think there was a 30-second delay. So it's like if I was to curse right now, then they would delay that, but I'm not going to do that to you guys. I'm sorry, Amanda. But yeah, if you have anything else you need, let me know. You can hit me up on social media. I'm at Robert Kaplinsky. If you're on Instagram, it's at Robert_Kaplinsky. But again, thank you for making time, and I appreciate all of you.